We're going to get started with the remainder of the session on innovation and technologies. We're moving now from the CyberGIS Gateway to the CyberGIS Toolkit. And our first presentation will be about PyCell. It will be by Rob Pahle and Sergio Ray.
All right, I'm Sergio Ray, and we're going to report on some of the work we've been doing on the parallel pPySAL project as part of the larger project, give you a little bit of overview of that, but then focus on a specific issue that we've been working on recently using parallel pPySAL, but embedding it in Rob's complex systems framework. And so the substantive application has to do with the realm of spatial econometrics. So this is one of the non-ologies that Jack talked about this morning, social sciences. But we're going to see that this has implications for another case where cyber infrastructure can help scientists in those domains. So I'll give you a brief overview of pPySAL, talk about the substantive issues, and then Rob will talk to you about our implementation. For those of you who don't know what pPySAL is, it's a Python spatial analysis library that we released in 2010, right before the project started. So we just released our 9th version. We release every 6 months. And we're up to about 70,000 downloads. So this project's been instrumental in helping us do things that otherwise we probably would not have been able to do. It covers a pretty wide swath of the spatial analytical realm, anything from spatial econometrics to spatial weights, computational geometry, spatial clustering, regionalization problems, exploratory spatial data analysis, and space-time or spatial dynamics. We're very proud that we've been picked up by the high-performance community in scientific Python. I was just at the SciPy conference last month, and now we are distributed with the 2 leading scientific Python distributions, Anaconda and Enthought. The parallel pPySAL project had its origins in this cyber infrastructure project. When we started pPySAL, we were thinking about a social scientist working with an SMP machine, not even exploiting the SMP machine, just using their desktop, and we wanted to facilitate the dissemination of spatial analytical methods to those problem domains. But as part of this project, we've been using pPySAL as a test case to see what is involved in moving this code that was developed in the non-HPC environment into HPC environments via the gateway and Big Iron. And we've learned quite a bit in the process. We started targeting different pieces of the library. We've built parallel contiguity builders for spatial inputs that don't have topology on them. The regionalization problems, we have a max-P version that's parallel. Lisa statistics, parallel Lisa, that was one of the first projects we did here with our colleagues at Urbana. Some map classifiers, Fisher-Jenks optimal algorithm, we parallelize that. And then in the econometrics realm, spatial regime models run in different flavors of parallelization. So this has been quite a learning process for us. Unfortunately, there's bad news. I thought it would be as simple as import parallel and the library would work, take advantage of all the hardware we had at our disposal, but that's not the case. And it turns out we're slow to learn this. Other communities have discovered this, that there's no holy grail of automatic parallelization, at least for realistic problems that we faced. So what I think we need, and what we have a lot of scars, is to identify the dead ends that didn't work and publicize that so that other folks who work in these endeavors don't make the same mistakes we did. But we need a way to capture that. So the substantive application that we're using here to illustrate this is using one module in pPySAL, the spatial econometrics module, SPReg. Last year we put that into the CG pPySAL part in the gateway with Shaowen's group. Here we're looking at a slightly different problem that eventually will also go in the gateway, and it has to do with specification searches. So in mainstream econometrics and spatial econometrics, we're looking at estimating a model and trying to come up with a final model. So what's that process like? And there's 2 dominant strategies. There's the short to long model, or specific to general, where you start with a classic spatial model, you estimate the model, and you carry out a series of diagnostic tests that guide you to the final model. There's an alternative strategy called general to specific, where you start with a comprehensive model that you estimate, and you test restrictions backwards to try and arrive at the, quote, true model. And these are competing strategies that have been looked at quite a bit in the econometric literature. We're going to look at the specific to general here because it's the one that my colleague Luke Anselin has developed most of the diagnostic tests for. And this is the schematic of the process. You start with a classic OLS regression. You carry out Lagrange multiplier test. And based on whether those tests are significant, you branch and continue through either carrying out new tests or ultimately estimating a model that's a leaf at the bottom of the decision tree. This is the simple version. The one we're actually implementing is much bigger, and you'll see it. Well, you won't be able to see it because it's too complex, but you get an impression for how complex it is in a second. As an aside, we've taken the SPReg, pieces of the SPReg module, the spatial econometrics module, in conjunction with our colleagues at Esri. We've built a toolbox that should be out shortly. It's actually in Esri's hands now. That opens up some of these applications to advanced spatial econometrics to ArcGIS. Okay, so this is actually the decision tree in text for a comprehensive, specific to general specification search. So there's a lot of branches here that would guide the econometrician to their final model that would get reported in the paper. And what we're doing here to leverage cyber infrastructure is we're using speculative parallelism. So rather than sequentially estimating the branch that you're ultimately going to end up in, we're going to estimate all possible models simultaneously using parallelism and then give the user the one that the tree tells them to get to. That's the idea here. Now this case we're looking here is fairly complex, but they can get even more complex. So you would be in the realm of a large model space if you think about it in those terms. We're using PyNPI on the cluster to set this up. Now, are there any econometricians in the room? Because this community, CyberGIS, sees right away the benefits for this, right? We are going to trade this elegant theory for specification searches and replace it with brute force. Well, it's not brute force. It's parallel computation, right? So we're gaining there big time. We're getting to explore the whole model space and not just one branch of the tree. But the econometricians, at least the pure ones, don't like this because that elegant theory was hard won that would guide the modeler to their final specification. And they also take a fairly dim view of data mining and machine learning as a way to come up with your final model. So there are some tensions here, particularly for social scientists, moving into this realm that I think we need to be a lot more cognizant of than perhaps we are. And with that, I'll turn over to Rob.
Hi, everybody. So we have the back end, which basically calculates this parallel tree and gives you the solution of that particular problem. In order to visualize this, we use a framework here, which we call the complex systems framework. I put up a schematic on this so just to give you a taste of what actually happens behind the scenes. So this is a componentized model all across. So at the bottom is data, which could come from various sources. Then we wrap models, one of which is, in this case, this SP Autoreg. Then there is a workflow manager where you could string together several models, and in the end, we basically output multi-screen, multi-user collaborative environments that you could use. So here is our kind of infrastructure that we're using at the moment to test. So in the front here, the internet, basically a web browser client, goes through some balancer nodes, which go to a bunch of web servers, which basically would provide the GUI, the visual interface. Behind that, we're sending the actual task to some login nodes, and then at the end is a parallel cluster. So this interesting thing here is what I call ResearchNet. I think this is where the interface is to CyberGIS. I think the interesting thing that we've heard over again is that we might have a repository of various CyberGIS tools, which then could be used in various ways. So the complex systems framework would be one user of all these tools that we can amass. So question is, how do we find the right tool and how do we use it in the right way? But at least from a technical infrastructure, at this point we would hand off, right, and run the system somewhere in the CyberGIS realm. Okay, so here is a screenshot of the interface. Since this is multi-user, multi-screen, you can actually modify the interface however you want. in this particular case, we selected an uploader, so you drag your shapefile up. Once you have a data set, unfortunately, this is not very sharp. So I encourage you to come by. We can show you this live as a demo this afternoon or evening. You can select your data set, you select your dependent variables, then your analytical variables, basically the independent variables. Here you verify that, and then you get immediately basically maps and visuals of this. We have also put in classification schemes, so you can look at the data in various ways. You get the output of all the analytics, and at the same time, and this runs on a second screen, you get actually the pathway that is taken. So here you see a graphical representation of the same tree that Serge showed a little earlier, and then depending on which models were taken, basically you get the results. So this is your decision tree that is just a visual representation of it. And then just to give you a taste how this looks behind the scene, so this would be the representation of what we're actually doing. It's a little messy, but that's the beauty, right? So you can put components in and remove components wherever you like. So the tree we added just 2 days ago, just for you to understand what's actually happening behind the scenes, and we just put a tree module up in addition. Oops, wrong direction. Which is just here, which we connect to our job, and then you can see the tree. So this allows you to flexibly modify your interface. And the interesting thing also, what Mary talked about, for interaction with a large audience, you can actually modify your interface in such a way that it makes sense to that audience and experiment with that. Okay.
Yeah, so that's where we are right now. The next steps are thinking about more comprehensive specification searches, so putting a hybrid model where it's a combination of the short versus full. And you might think, well, isn't this stepwise regression? It's not stepwise regression, but it's akin to that, if you want to think about that. So then all possible combinations of models that one could estimate that could be parallelized. Uncertainty in the choice of the spatial weights, obviously, are important to us. So there's a lot to do there in terms of enhancing the tree, if you will. And then obviously integrating this so that it's available to, through the gateway to a wider domain of scientists. And come see the demo, because it actually runs. Thanks.
Question for him while we're changing setup. Go ahead, Dan.
Oh, there's a question.
Got one over here?
Very interesting point on that tension. Could you elaborate more how that tension came about?
The tension is not all econometricians, but classical econometricians would take a dim view at theory that's data instigated, right? Which is maybe foreign to a lot of us in this community. But in that community, there's a long literature that's hostile to, say, stepwise regression as a simple case, in that it's dismissed as measurement without theory. Slowly changing.
Thank you. Let's go on to the next presentation on the CyberGIS Toolkit. We have Yan Liu on parallel genetic algorithm for optimization. Yan?
Thank you, Lee. Good afternoon. I'm Yan Liu, the technical coordinator of the CyberGIS Center at the University of Illinois. Today I'm going to present a software piece in the CyberGIS Toolkit. It is a parallel genetic algorithm library we use for spatial optimization. This morning, Shaowen has introduced briefly what do we do with this library. I'm going to give the geeky part of the work, but it does have a tie with a social science application that may be of your interest. So I'll briefly introduce the concept of parallel genetic algorithm, and the main focus of the talk is to resolve the scalability issue, and we'll report some of the performance results and discuss some of the ongoing development work. So this is the architecture of this library. We mainly solve two kinds of optimization problems. One is assignment problem, the other is partitioning problem. Depending on whether the problem has a spatial constraint, we developed two sets of genetic algorithm operators. GA stands for genetic algorithm. Because of the constraint from the spatial world, these operators are significantly different from the conventional GA operators. The main contribution so far we have done is to contribute a scalable part, the parallel GA component, which consists of three parallel GA operators and buffer management and parallelism control for better parallelism on large-scale supercomputers. This library mainly targets the deployment on supercomputers, but imagine in the future your laptop has hundreds or even thousands of cores. That's the software that you can run to actually speed up the GA process. So in general, a very brief background about the combinatorial optimization problem. Basically, you want to optimize one objective or multiple objective functions here, but you have a bunch of constraints expressed in mathematical formula like this. If the problem variable is not integers, you have actually a lot of ways to solve it quickly to optimal. But if the problem variable or a subset of problem variables are integers, it becomes nasty because of the so-called computational complexity of NP hard. That's in computer science background term. That basically says you cannot just add more processors in order to actually solve a bigger problem. Adding processors is not sufficient. The computing time actually grows exponentially. So this actually indicates two, I'll give you an example. This is the example Shaowen presented this morning. It's the political redistricting. It's in social science, but it's a computational problem. So the problem basically targets to actually partition a set of political units into a few districts for voting or election purpose. And the number of possible solutions is huge. It's the Stirling number of the second kind, which grows exponentially as the number of units grows. Take a look at the state of Minnesota. It has 250,000 census blocks. If you want to solve this problem and partition this state of Minnesota at the census block level into 8 districts, you have a numerous number of solutions to consider. And even you have a very good sequential algorithm, that's not enough because of the problem size. That's where parallel computing is needed. So it's very hard to find the optimal solution. So people develop a lot of a rich set of heuristics in operations research domain. And one of them belongs to a meta-heuristic, meaning it's not as problem specific. It's generally applicable to any problem solving. One of the efficient heuristic is called genetic algorithm. This Shaowen mentioned that it has a very simple principle of the survival of the fittest. It actually has mainly has 2 steps. You have to encode the problem. For example, if you want to partition 9 units into 3 districts, this is probably the way you actually represent it. But you have to encode it in the chromosome. Then you actually do an iterative approach in the GA iterations to actually find out the good solutions. You start with the population, which is a set of initial solutions. Then in each iteration, you can select the parent solutions from the population, do some reproduction operators such as crossover and mutation, and produce child solutions. If the child solution has better quality than some of the worst solutions in the population, you replace them and go to the next iteration until it converges. It is quite straightforward to actually parallelize the GA. You can parallelize in a lot of ways. Given that you have a bunch of processors interconnected through a network topology, you can actually, if you want to put the parallelization on the selection step, you can actually get to the parents from the neighboring processes. If your fitness evaluation part is computing intensive, you can do the parallelization on that part alone. And the popular approach is called coarse-grained PGA. Actually does the parallelization when you actually do the replacement. If you have multiple processes, each process actually runs an independent GA process. From time to time, you actually exchange the solutions from, to your neighbors. And there are a bunch of, we call this a migration. There are a bunch of parameters you need to set to decide to determine when to migrate, how many solutions to migrate. Well, by the time we look at the parallel genetic algorithm library, we found that actually none of them could scale to more than 1,000 processors. We then studied why, and that's the main challenge we faced and we resolved. That's the second part I want to talk about, the scalability. So it turns out that when you do this migration, you have to keep every process on the same pace. Let's imagine that they actually use a global barrier provided by the underlying parallel computing library. Let's imagine the global barrier is like a traffic light you put on the road. And you have a road, and the number of lanes on the road is equal to the number of processes. So if you only have 100 lanes, you put a traffic light there, you turn the light to red, every car on the road would stop at the traffic light. At there, you actually do the migration. After that, you turn it to green, and the cars go forward into the next GA iteration. Well, but thinking about, you have a road that with 16,000 lanes. It's a big road, and you ask everyone to stop at the traffic light, do the migration, then resume the GA computation. And that's the bottleneck. We did an experiment on Blue Waters supercomputer using 16,000 processors. And turns out that actually, just for the synchronization part, it took 41.39% of the execution time to do that, just that. That's really bad. So the solution is pretty straightforward. You just break the global barrier, but it opens the doors to a very good but a nasty scenario. You don't reinforce the global barrier. That means every car can do the send and receive anytime. And you have to actually deal with a nasty scenario that has been hidden by the parallel computing library now, which is the buffer management. So we have to deal with that because you imagine a road without traffic light, that you probably can imagine a lot of accidents can happen. And depending on how serious the accident is, you can actually crash your own application. So it's just a little bit more explanation on the buffer management. You probably don't know that actually for any communication between computers, it goes across multiple layers of buffers. From your network card on the laptop to the network protocols to the parallel computing library and eventually to the application. Now we don't reinforce the global barrier, so that means we have to actually know the buffer from the underlying buffering mechanisms. If we don't do it, any buffer at the system level got overflow, the whole application crashes. So that's what we need to do to carefully design the library. This is a math, but basically it says that these overflow problems cannot be completely avoided. But we can do our best to actually avoid the buffer flow problem from the cause that we set these parameters wrong. So basically, it says the sending buffer and the receiving buffer can overflow in the case that in some of the scenarios, we identified 3 scenarios and derived 2 theoretical conditions to guide the setting of the PGA library. With that, you can guarantee that if the application crashes, it's not because you set the PGA wrong. It's due to some system level error. And nowadays, actually, the system is built quite robust. It's not easy to crash the whole supercomputer. We implemented this using the non-blocking MPI functions, and it's scalable to 31,000 processors on Blue Waters, and it's part of the open source CyberGIS Toolkit now. I'll present some of the, I only have 1 minute, okay. That goes faster than I expected. So the performance study of this stochastic algorithm, the GA is kind of a stochastic algorithm, is a profound process. We have some research work going on there. This is the scalability diagram. We call it speed up. Basically means how fast you can run with more processors. The left part is the synchronous version. The right part is asynchronous. The black line is a linear speed up. So you can actually see we observe the superlinear speed up in this case. And the asynchronous, which breaks the global barrier, actually performs pretty good compared to the synchronous one. And the weak scaling basically compares whether your algorithm can handle a bigger problem if given more processors in the same amount of time. This diagram shows that we can actually achieve the different solution qualities with less time if given more processors. And with the marginal communication cost. For synchronized version, you can see the percentage of a cost, and this is asynchronous. This is a significant drop. We tested it on 131,000 processors on blue waters, and we achieved similar results. We even tested on heterogeneous supercomputer on Stampede at the Texas Supercomputer Center, Advanced Computer Center. And this supercomputer has both a fast, but fast host processor and a slower co-processors. And you can see synchronous version is quite sensitive to the architecture, but the asynchronous ones is not. So we have some ongoing work on the application. That involves development of spatial GA operators. I probably don't have time to illustrate those, but conventionally you do the binary crossing, and now you have to do graph computation, which is much more computationally intensive to combine the solutions into new ones. Similar case for mutation. As conclusion, we developed a very scalable PGA algorithm that can scale very well on supercomputers. Now we are taking good problems to work on large size problems in redistricting, and we're making progress, and we'll report back when we actually develop this spatial GA operators. And this is up for downloading, and I want to thank the funding agencies, our collaborators, and several major supercomputers that allow us to do the experiments. Thank you.
Questions for Ian?
Oh, sorry. Yes.
Go ahead. Question for Ian while Anand said it?
This is one of our efforts to actually provide.
Ian, can you repeat a little bit of the question?
Yeah, so the question was that how do we avoid the future buffering headaches if we have to deal with it again? Well, I guess the trend in computer science is to have a specific, there's a trend of research called the domain-specific language, DSL, that captures the general requirements, the parallel computing patterns. That's one way. By developing this library, we are trying to hide the handling of these buffering issues from the user, so that the application only need to know some parameters to tune with, but they don't need to worry about the underlying buffering because it's totally hidden from the architecture diagram.